What do you need for an equation of a line? 2 points or a point and a slope, right? A point and a slope usually will get us farther in terms of getting our equation down. So in general, you need a point and a slope. When you're talking about 3 dimensions, the idea of a slope is a little bit more complicated. So what we want to do is we want to change our idea of a slope instead of calling it a slope. If you imagine a point in space and a direction that you want to go, a direction vector, then you essentially have a line, right? You would just draw that line. So our first task is to come up with an equation of a line in 3 dimensions, and we'll be using the idea of vectors. So instead of looking at a slope, let's look at it from a parametric equation point of view. And from the parametric equation point of view, we can kind of go back and forth between parametric equations and vectors. We technically haven't studied vector functions yet. That's what we're going to study in the next chapter, but this is essentially what it is. If you have parametric equations and you combine it into 3 dimensions, even 2 dimensions, you combine it into one vector looking function with components, then you have a vector function. All right, a line in 3 dimensions can be defined with a point and a direction. A line can be described as follows. So if you have a point P, or P naught, and then a direction A1, A2, A3, so a direction A that's given by A1, A2, A3, then for any point P, some random point x, y, z, P, the vector P naught going into that direction P is equivalent to some scalar multiple of A. Does that make sense? So what they're saying is that if you want that line, let me move my line here. If you want this line, or if you want this vector to be on that point so that you have a line, then any point on this line is going to be, can be described by going to this vector, or to this point P naught, and extending this vector A by some scalar multiple to whatever point you're looking at. Okay, so that idea might be a little confusing, but what we want to do in general is to get that equation of a line, what we're going to want to do is, if you're in 3 dimensions, what we want to do is we want to, let's see, to get to any point on this line, what we want to do is first get to that line, to this point, that known point, P naught, and then we're just going to add some scalar multiple of this A vector. Okay? So the P naught, if you remember, is equal to x naught, y naught, z naught, plus t times the A vector, which is A1, A2, A3. Now this is technically, I would like to think about this as a good function. This is a vector function. But we can break this down even further and do the addition and scalar multiplication of vectors where we just have one vector combining all those components together. So the first component would have x naught plus a1 times t. Your second component will have y naught plus a2 times t. And then your third component will have z naught plus a3 times t. So if you take each of these components apart separately, you have x of t, y of t, z of t, and those are your parametric equations. In 3 dimensions, you'll have 3 parametric equations. In 2 dimensions, you'll have 2. Okay? So those are your parametric equations, and that's where they would come from. They would come from a point and a direction. And dealing with it component-wise, you can break it up like this. Any questions? Let's see if we could do a quick example. I think I hopefully picked out good problems here. So this isn't quite your homework. This is one of those things that has a bunch of problems. Let's try this example over here. Find a vector equation and a parametric equation of the line. I don't know why they want both. It's kind of saying the same thing. Oh, maybe it's a little bit different. All right, let's see. Let's find a vector equation and a parametric equation of a line going through the points 8, -9, and 4. And it's the direction vector. If it's parallel to a vector, that means that that's the direction it's going. Because you know you can move that vector around. You just put the tail of that vector on that point, then you'll get that line that we're talking about. So really, if we have the point and the direction, I think we're done, right? All you have to do is put this point, make it into a vector, make it look like a vector, 8, -9, and 4, and then you add t times the direction that you're going, 1, 3, -2/3. Right? And then if you want to break that up into different components so that you can identify the parametric equations, you can just get the first component together. That would be 8 plus 1t. That's the x component. The y component would be -9 plus 3t. And then the z component would be 4 minus 2/3 t. I think that should be good. Let's try putting it exactly how it's written up there and see what this WebAssign says. So this is when you start playing with vectors a little bit more. You can use ij's, k's if you want, but I think I prefer to use the vector notation here. So it's 8 minus 9, 4. How do you close this off? Oh, there we go. T times another vector, and this vector is a direction vector. 1, 3, minus 2/3. And then for this, we put the components together 8 plus 1t, comma, minus 9 plus 3t, comma, 4 minus 2/3 t. So hopefully it'll take that. And then it might be good to see a visual of this. You guys want to see the visual? Let's see if we can see it on a graphing program. All right, good. It's good to have those check marks up. All right, so I'm going to start with a point, and the point is 8 minus 9 and 4. Can't see it. There it goes. Whoa, that's a big point. Now the vector in this particular program, to be able to write the vector, you're going to have to put the tail and then the head. So if we're talking about the vector 1, 3, negative 2/3, that vector, you can visualize that vector as a vector in standard position pointing to the point 1, 3, negative 2/3. So if I put it in standard position, that means the tail has to be 0, 0, 0. So 1, 3, minus 2/3. So this is your vector. Oops. And this is your point. But we want that vector to start at the point, right? So let's put that vector, let's make that vector start at that point. So what I'm going to do is I'm going to take this vector and then just translate it. If I translate it, that means I have to add the point to it. Does that make sense? I have to add the point to the head, to the tail, so that it looks like it's translated. And the point, what was the point again? What was it? 8, negative 9, and 4. So I'm going to have to add it here as well. So now I have that vector going from the point. You see that blue vector? It's attached to the point. So these two vectors are parallel because they're the same vector, they just got translated. Now let's draw that line. What was the equation of that line? I guess it doesn't, I probably want the equation of the line to look like parametric equations, but I think I could do it in regular equations. Oops. So to do an equation of a line here in 3 dimensions in parametric equations, I need x, y, z equals, and then I need the equation. So I can write the equation either in parametric form, where I have the x, the y, and the z in the different slots, or I can write it in vector form. So in vector form, I just have the point plus t times the direction. Yellow. Should make it blue. So can't see it. You know what's going on? You know where that line is right now? Here. You know where that line is right now? It's on the point, and it only goes as far as a vector. Right? So far, it only goes as far as a vector. That's because my t goes from 0 to 1. So imagine this equation. Look at this equation. If t was equal to 0, what is it? You're exactly at that point. If t is equal to 1, you're at the point plus a length of that vector. Right? So to see this line a little bit more, if I just extend this to 2 and maybe extend this to -1, then there's my line coming out of that point passing through that vector. And it's up to your t parameter to extend to as far as you want on this line. So if we make it get really big, like -10 to 10, then you have that line. That line is defined by the point going to the point and extending it out according to the direction of your vector. Okay? Is that an okay visual? Did it work? For some of you. Boy, if you guys can understand what I'm doing up here, that's even better, because what I'm doing here, it looks like it's like computer science stuff, like putting in functions and stuff like that, but it's really the mathematics behind what's going on here. So even if you don't have this program, this graphing calculator program, you should try to imagine what I'm doing and try to understand it. All right, so that's our visual. I don't know if there's a good way to draw this representation. Yeah, that's probably not going to work. Oh well, we'll take a picture of this anyways and put it in our notes. Am I recording? Oh, yeah. Do you guys look at the notes anyways, by the way? Okay. All right. So that's one type of problem. And in general, if you can just find the direction that you want to go, then you got a point in a direction, then you're all done. This is almost as easy as a point-slope formula. In some cases, even easier, because you just drop it into the formula. So there's a couple of other interesting ones that aren't straightforward that might be good to look at as well. We got 6 and 7. This idea that it's perpendicular to a plane going to the origin. Let's do number 6. And with the information that we know about planes, hopefully you can answer this question. And maybe I'll just do the vector equation. So this time your point, a line going through the point 1, 0, 3, and then perpendicular to a plane, x plus 3y plus z is equal to 3. And this is your plane, and your point is somewhere. Let's just say it's over here somewhere. So you essentially want a line that's perpendicular to the plane passing through that point. So you want a line that looks like that. So what do you need for an equation of a line? Point and a, so the slope is what you used to say back in algebra. Now that you're in Calc 3, what do you need for an equation of a line? Point and a direction. So you start with a point, and then you add t times the direction, you're done. Okay? What's the direction that we're looking for here? Perpendicular to the plane. Can you tell me a vector perpendicular to the plane? The normal vector. Sure, that'll work. Now let me ask you this. Can you find the normal vector? Okay, we dug down to the equation of the plane. We broke it up to different kind of components and stuff. And take a stab at it. Take a guess. It's kind of staring you in the face, so to speak. Anybody want to yell out the normal vector? What? Close.
Is it 0, 3, 0?
No. 1, 3, 1. So what were you looking at, Moises? It's perpendicular, so it's a normal. And the normal comes from, Cameron? This coefficients. Remember, the left-hand side was the normal vector dotted with x, y, z. If you imagine this equation, x plus 3y plus z is equal to 3, and you undot the left-hand side, so to speak, then the coefficients that are sitting in front there will make up your normal vector. So your n is equal to 1, 3, 1. So it's really, it's that simple. It's 1, 3, 1. There you go. Now that you know that, you have a point and a direction, you're done. Right? So the point, 1, 2, 3, or 1, 0, 3. Uh-oh, I'm writing it like I'm in linear algebra or something. Sorry. You guys understand what I'm writing? So just change these column matrices into vector-looking things, and then put that in your answer bar, and you're all done. Okay. All right. What's next? So these equations, we've seen what we are calling vector form, and we've seen what we're calling parametric form, something that we've seen before. But you can also look at it in this other form called symmetric equations. And actually, before we take a look at this, before I write this down, let's take a look at an example in 2 dimensions. Because we could do this in 2 dimensions, right? That's one of the things that I was saying. So let's take a look at lines in 2 dimensions real quick, a little detour. And let's take a look at, let's say we have a point, 1, 0. And then I want to go in a direction 1, 1. So let me imagine that. Let me look at it geometrically first. At the point 1, 0, that's 1, 0 right here. And then in a direction of 1, 1. Now I want this direction, but to make sense out of this, I'm going to translate this over to this point so that that's the line that I'm looking for. And we can find the equation of that line, right? I think this thing crosses the y-axis at -1. It has slope 1, so I think it's x minus 1 or something. But let's, I jumped the gun there. So let's do this in parametric form first. So your R of t, your vector form, is going to look like a point, 1, 0, plus t times the direction, 1, 1. And then you can write this in parametric form as 1 plus 1 times t, and then 0 plus 1 times t. So this is your x and your y. Right? So now, when we were studying parametric equations, we went through this process called eliminating the variable to see if we can just find the relationship between x and y without the t. So let's try to do that. How do we do that again? We isolate the t. So let's get t by itself here. T is equal to x minus 1. And then here, t is just equal to y. So let's put those two together. Y is equal to x minus 1. Right? So isn't that what I said? It has a slope of 1, a y-intercept of -1, so that totally makes sense. And so if we eliminate the variable, we're able to write this as a relationship between x and y. It turns out that in 3 dimensions, we have a third variable involved. And so with that third variable involved, if you want to find the equation of a line, you have to have an equation that has 3 parts to it. Okay? So here's what's going to happen. In 3D, we have what's called symmetric equations, where we follow the same process and then we come up with this equation with 3 sides, one with an x, one with a y, and one with a z. And that is going to involve the same thing that we did, which is to isolate the variables and set them all equal to each other. Except when we set them all equal to each other, there's 3 of them, so we just have 3 parts to this equation. So if you imagine coming from x is equal to x naught plus a1 times t, y is equal to y naught plus a2 times t, and z is equal to z naught plus a3 times t. If you solve for t for each one of them, and then set them all equal to each other, and then this is what you're going to get. So what I need from you to be able to do is to go from a set of parametric equations into symmetric equations, and then I also need you to be able to go backwards. If you have symmetric equations, see if you can find the parametric equations. Okay? Lauren.
And the point A1 is a point A, and it's the x, y, and z components of it?
No, the point is x naught, y naught, z naught, and then a1, a2, a3 is the direction.
Okay.
So let's make that clear here. Point is x naught, y naught, z naught, and then direction is a1, a2, a3. You know, I'm switching my notation with parentheses and those greater than, less than brackets. So I think I'm gonna do everything in parentheses. Okay, so that it's up to you to figure out if it's a point, if it's a vector, if it's a vector function. It's all just going to be in parentheses. Okay, so if you can start memorizing this or reapply it to a bunch of the problems that you guys are going to be doing, just remember the denominators here will be the components of your direction, and then whatever else is on top. Okay, questions? All right, I think we'll save doing an example of this when we do some other more complicated examples of things. So let's see what else my notes have to say. Skew, 2 lines in space. All right. So back in Algebra 2, or wherever you learned this, maybe it was even in Algebra 1, if you have two lines, if you have two equations of lines, two lines, then they follow one of three things. One of three things can happen, right? Like if you throw two sticks in the air and then make it land on the ground, it's either going to intersect at exactly one point, it's going to be parallel to each other, or the weird case, they would land right on top of each other and they're the exact same line, right? So those are the two or the three things that could possibly happen when you throw two sticks and make it land on a flat two-dimensional plane. In 3 dimensions, it's a little bit different. You can't throw, unless you can imagine throwing a couple of sticks and make it freeze in the air. That would be cool. That's lightsaber sound. So the two things that can happen, or three things that can happen, and we're not counting if the two sticks just actually attach to each other and they're the same line. So if you count that, then that's 4 things. But in general, what you can look at is that either the two lines are parallel, and you throw it up in the air or freeze it in the air, the two lines are parallel, they intersect at exactly one point, or they are what you call skew. Skew. So 2 lines are parallel, the lines look like this, 2 lines intersect, and 2 lines are skew means they're not parallel, but they don't intersect. And that makes sense in 3 dimensions, right? Can you imagine that? That makes sense in 3 dimensions. Just like that, right? They don't intersect. They're certainly not parallel. They are skew. So when that happens, they're skew. So what we're interested in doing is, if you have equations of 2 lines, we want to know, do they intersect, are they parallel, or are they skew? So we have, let's just jump into a problem with that. Let's see, is it 12, 13, or 16? Okay, here's one. Oh, there's a type of problem that I skipped. We need to go back and do that. But here's one where you determine if 2 lines are parallel, skew, or if they intersect. And in general, that's the order that you want to look at. First you check if they're parallel, and then after that, if they're not parallel, then you check if they intersect. Oh, that's not the order then. First you check they're parallel, and then check to see if they intersect, and then check to see if they're skew. All right. So here are the 2 lines, and in terms of the line and finding out if they're parallel, what would be a good thing to look for in the line? The direction of the line, right? If the directions are going in the same direction or even opposite directions, then they're parallel. So let's see if we can remember, based on what you know so far, let's see if we can extract the direction here. So direction for the first line, I want a vector out of this. Do you remember which the direction is? Is it 9, 12, 3, or is it 6, negative 3, 9? It's the one with a T, remember? The direction is the one with a T. So I'm looking at 6, negative 3, and 9. So let's compare that to the direction of the second one. They don't have T anymore. They have S. Well, we'll talk about that later. But S is just the parameter. So I guess they don't want to mix up the s and the t, or the t for one variable and the t for one line and the t for the other line. So they just go ahead and call it s. So if we
Now, for the sake of this case, because they don't give us any parameters as part of what t and s are, we can just assume they're going from negative infinity.
yeah, you can assume that they're going from negative infinity to positive infinity. So we have 8, negative 4, and 10. Now, how are we going to know if they're parallel? There's a couple ways to do this. One way to do this that I think is more difficult than easy, more difficult, is that if we take the cross product, remember the cross product is equal to 0 if the angle between them is either 0 or 180 degrees, right? So if the angle is 0 or 180 degrees, then there would be parallel. So if we take the cross of this and we get 0, then they must be parallel. I think that's a little bit more overkill. You can do it that way if you want. But the other way to do it is that if they're a scalar multiple of each other, then they're essentially parallel. So what you could do is you could put 6, negative 3, 9 equal to some scalar, 8, negative 4, and 10. And that scalar doesn't have to be here. It could be on the other side. And for that matter, the scalar can be on both sides to see if you can factor or multiply or do something to make these two things equal just by changing these variables, these scalars. Okay? So my idea is to just see if I can factor anything out that would make this look the same. So if I factor out like a 3, it looks like a 3 would factor out nicely. 3, and then we still need to scale it. 3k is equal to 2, negative 1, 3. And if I do this factoring here also, and then I get 2, negative 1, 3, then they must be. Take a 2 out, you get a 4, a 2, and a 5, negative 2. Now, can I change the k, the kappa, or the lambda into anything that would make this equal? Doesn't look like it, right? So, no k or lambda to make this equation work. So from here we can conclude not parallel. Okay? So we can cross that out. The next thing to check is that if they intersect. Now these are parametric equations. So because they're parametric equations, they move around in space according to their parameter t or their parameter s. And the reason why they changed one to s instead of keeping them both t, is that if they do intersect, maybe this line is going to get to this point when t is equal to 5, and maybe this line is going to get to that point where they intersect when s is equal to something different. So that's why they have the two different variables for this. And so when we set this up, usually when we look for intersections, we set some equations equal to each other. And so the most common thing that would make sense to us, the most common sense thing for us to do, is to set all the x's equal to each other, the y's equal to each other, and the z's equal to each other. When we do that, what do we get? We're going to get 9 plus 6t is equal to 2 plus 8s. We're going to get 12 minus 3t is equal to 3 plus 9, is equal to 6 minus 4s. And then we're going to get 3 plus 9t is equal to 8 plus 10s. So we're going to get 3 equations and 2 unknowns. And so the way to solve for this is you can use matrices, you can use linear algebra. The way we're going to think about doing this is we're going to solve for the s and the t between 2 of the 3 equations. And then after we get our solution for the s and the t there, we're going to plug it into the 3rd equation to see if it'll still work. Okay? That's just one way to do it. And you can, like I said, use linear algebra methods to solve for the other stuff if you want. But let's do it like this. And for that, I think I'm kind of used to having all the s's and t's on one side, so I'm going to bring all the s's and t's on one side. I'll bring it over to the left side here. We got 6t minus 8s, and then the constants will go on the other side. So I have 2 minus 9, I think that's negative 7. And then I'll do the same thing for the second equation. I have a minus 3t plus 4s is equal to, I have a 6, and then I want to subtract 12. 6 minus 12 is negative 6. So I have 2 equations, 2 unknowns. It's even in a nice format that I am comfortable with from all the algebra work that I've done in the past. So I can like maybe multiply the second equation by 2 or something like that and add, I don't know, something like that. The what? Oh, well, maybe that's the thing that happened. So if we take this and then we would get 6t minus 6t, negative 8t plus, or negative 8s plus 8s, and then negative 7 plus negative 12, whatever. It's non-zero. What is it? Negative 7? Negative 19, thank you. Okay? So here we see a contradiction, so it doesn't work. Does not. And remember, what we're looking for is to see if they intersect. So it doesn't work, so it looks like the graphs don't intersect. The lines do not intersect. So what you need to do here in this process is, if we would have gotten an answer for s and t, you still need to plug it back into the 3rd equation, and then that has to work. If you found s and t and plug it into the 3rd equation, it didn't work, then they don't intersect. So there's a lot of chances for this thing to not intersect. Okay? So if they're not parallel and they don't intersect, then you only have one thing left, and that's skew. Okay? All right. I had in my notes that I should do 12 and 13. It's 150. Let's just do it real quick. There's nothing quick about this. We'll have to do it next time. All right, so I don't have any homework due this weekend because it's, oh, that's 10.6. I was talking about Chapter 12. Chapter 12, I meant to have some Chapter 12 stuff due already, but since it's a holiday, I decided not to do it. So so we started on 12.5. So next Sunday, everything up to 12.4 will be due. Okay? And then 12.5 homework will be due the following. I'll give us some time to digest this stuff. All right, have a good weekend. Happy Valentine's and President's Day and all that stuff.